Hi everyone, my name is Leo Scada from University of Nevada, Las Vegas. I'm excited to welcome you to the next series of webinars focusing on fourth gravitational wave transient catalog. Before we get started, we have some issues to have some of the panelists. So please hold on for a moment to make some adjustments for our end. We just need to make sure that all the panelists are joining.
Okay, and that should be everyone, I believe.
Great.
Yes.
So let's get started. Today, we're going to be hearing about population properties of merging compact binaries from GWTC 4. With that, I would like to introduce Aditya Kumar, who is going to be host this webinar today. So please take it away.
Yes, thanks, Leo, and thanks, Casey, for setting this up. This is a webinar on the population properties of merging compact binaries from GWTC4. We'll learn today about what the ensemble of the catalog looks like at the population level and how we can learn about astrophysics from these kinds of population level properties. So this is the link to the paper. You might have already seen it in archive already. You can also access it on the LIGO public DCC by following this link. Just before we start, there is one other webinar that's going to happen in a week's time. So today, obviously, we'll be learning about the population properties of merging compact binaries. But on the 16th, there will be a webinar by the people who do cosmology. So essentially constraints on the cosmic expansion rate and modified gravitational wave propagation from GWTC4. Stay tuned for that webinar because that will also have a lot of interesting things to do with populations as well. Great. So let me quickly run through the list of panelists and speakers we have for you today. We'll have a total of 6 people who will be taking turns to speak and answer your questions today. So we have Ben Farr from the University of Oregon, Shio Sakon from Pennsylvania State University, Jack Heinzel from MIT, Massachusetts Institute of Technology, Debatri Chattopadhyay from Northwestern University. I'm Aditya Vijayakumar. I work at the Canadian Institute for Theoretical Astrophysics, and we have Simona Miller, who's from the California Institute of Technology. Great. With that introduction, let's take it away. Ben, I think you go first.
Yeah, it's great to be here. So I'm going to kind of kick off the paper and start off with describing the structure and then get in a bit to the motivation and our methodology for how we go about constraining the population of compact binaries that we are seeing. So here you can see the abstract. I'm not going to go into the details there yet, but the overall structure of the paper, we give an introduction, then we give a light coverage of the methods that we employ, and then we look at the population from a bunch of different perspectives. One, looking across the full mass spectrum, including all 3 types of sources that we're sensitive to: binary neutron star black hole, and black hole binaries. Then we shift our focus to just looking at the astrophysics that we can constrain from neutron star containing mergers, binary neutron star and neutron star black hole events. And then we turn our focus to the most populated category of compact binary that we have in the catalog, which are binary black holes. And then we wrap up with some conclusions. So the gravitational wave transient catalog is fundamentally a probabilistic catalog. We don't get certain estimates of the properties of individual binaries that we detect. We get 15-dimensional complex distributions that extract as much information from the strain data from the actual observations made by the LIGO Virgo Kagra detectors as we can. And the job of inferring the underlying astrophysical distributions involves using all of that information in a self-consistent way. Not only that, we see these events through the effects of the sensitivity of our detectors. We are not uniformly sensitive to binaries across the parameter space. We are, for example, more sensitive to massive binaries than less massive binaries. And so to properly estimate the underlying astrophysical distribution, we have to account for these selection effects when we go about our population inference. So to do all of this in a self-consistent way, the community has developed this suite of Bayesian hierarchical inference tools to both properly characterize and account for our selection effects at the same time as using all of the information that the strain data has to offer on each event in the catalog. All right, next slide. So we employ lots of different models when we go about characterizing the astrophysical distribution. They largely fall under two umbrellas of model types. One we call strongly modeled, which are we would also describe as parametric. So think simple-ish descriptions of the underlying population, like power laws or broken power laws. We turn up the complexity as the fidelity of the catalog improves. So with the most recent catalog, for example, when we look at the mass distribution, we consider broken power laws with multiple peaks present in the data, and then we use these models to constrain the data. The alternative are what we call weakly models, or maybe non-parametric models or semi-parametric models. These are models that are actually highly parametric, that have lots of flexibility. And so they're our attempt to look at the data with eyes wide open and look for features we may not have anticipated before the analysis of the catalog. And so these two models are complementary, these two types of models. One, the parametric or strongly modeled approaches let us do our best to constrain the data with the limited information that we have. If they are an accurate description of the underlying astrophysical distribution, they're going to give us the most precise recovery of features like the presence of peaks and the properties of those peaks, whereas the weakly modeled approaches give us the ability to find things that we weren't necessarily expecting. All right, next slide. So finally, we also analyze two subsets of the catalog. We don't look at the entirety of the catalog with all of our models. We take two different cuts through this catalog. The first being the complete mass spectrum, so including all events, including neutron star containing events. For this analysis of the catalog, since we have less neutron star containing events than binary black hole events, we make a more conservative threshold on the astrophysical significance of the events in the catalog, making a cut less than 0.25 false alarm rate per year. That cut on the catalog leaves 2 binary neutron star mergers, 3 NSBH mergers, neutron star black hole mergers, and 138 binary black hole mergers. Now, to get basically the same level of possible contamination, possible number of confused events for astrophysical events in the catalog, when we look at the binary black hole population in great detail, then by excluding neutron star containing events, we can take a less conservative cut on the significance of the events that we consider. We go to a false alarm rate of 1 per year, or the possibility of 1 noise event getting in the data per year. And with that cut, we look at 153 binary black hole systems when we are constraining the properties of just the binary black hole population. All right.
Yes, I'll talk a little bit about the data set that we used for our analyses. When we say GWTC, we include all of the data from O1 to O4A. So for GWTC4, we're including everything from O1 to O4A. However, we are excluding the engineering run portion, and engineering runs are used for LIGO and Virgo detectors to collect data prior to the official start of the observing run to test how the detectors are, the sensitivity of the detectors, and to let the pipelines collect a little bit of data before the run officially starts. For GWTC4, there was an NSBH candidate that was detected during this engineering run before the start of O4A. GWTC4 itself does contain this engineering run data as well as this NSBH event. However, the analyses used for this population inference, we decided not to include this engineering run data as well as this event to minimize bias. I'll mention a little bit about the selection criteria for the gravitational wave events that are included. As Ben has mentioned, we use a significance threshold of FAR of 1 per year or less, with a stricter FAR threshold for events that include neutron stars. However, we do exclude one event, GW230630. This has been deemed to be of instrumental origin So although it is included in GWTC4, we do not include it in our analyses.
All right, yeah, thanks, Xiao. Yeah, so I'll be talking about our constraints on the full population across all merging binary compact objects. So this is including the neutron star containing events that Ben and Xiao were mentioning. And as Ben also mentioned, we're going to use two different approaches to modeling the population. We have the strong approach on the left, which is this full pop 4.0. And on the right, we have our weakly modeled approach, which is a binned Gaussian process or just BGP. And so in each panel here, what I'm showing is the inferred merger rate across the joint distribution of primary masses and secondary masses. Primary masses are defined to be the heavier object in the system, so we exclude out this upper triangular region by definition. If you go to the next slide, we can see that we have a number of different features jumping out in the joint distribution. In the lower left-hand corner at around 1 to 2 solar masses for both compact objects in the system, these are consistent with our binary neutron star mergers. So these are the two binary neutron stars that we included in the catalog. This is telling us what the intrinsic merger rate in the universe is for this source class. And then in the right-hand lower corner of the joint distribution, we can see the primary mass is too heavy to be a neutron star, but the secondary masses are still around 1 to 2 solar masses. And so these are our neutron star black hole mergers. And then finally, in the upper right-hand corner, we see both objects are now too heavy to be a neutron star, and so these are the binary black hole mergers, which form the majority of our catalog. Next slide. Yeah, so one of the important things that we can study when we include all different source classes in our population is we can study what is the population of merging compact binaries at the transition between neutron stars and black holes. And this has been something of a lot of historical interest, because when you use electromagnetic telescopes to try and characterize the distribution of neutron star masses, you see there is a maximum at around 2 and a bit solar masses. And then when you look at the distribution of black holes, you see that there seems to be a minimum black hole mass at around 5 or 6 solar masses. So there seems to be maybe a order of magnitude suppression in the merger rate of compact objects between this maximum neutron star mass and the minimum black hole mass, or maybe there's just a gap completely. Now with gravitational waves, we've observed a couple of events that seem to have one of the compact objects lie in this purported gap between neutron stars and black holes. And so consistent with the observation of these events, then when we look at what our population reconstruction tells us about the merger rate at the transition between neutron stars and black holes, we see that there does seem to be a suppressed merger rate, but it doesn't go all the way to 0. And straddling this suppressed merger rate is a peak in the merger rate at neutron star masses, and another peak at black hole masses around 9 to 10 solar masses. Okay, and then the final thing I wanted to comment on is the merger rate of binary neutron stars. So unfortunately, we did not see any new binary neutron star mergers in O4A. But our sensitive time volume to mergers in this source class has increased by about a factor of 2. So consistent with that, then we have to update our understanding of what the intrinsic merger rate is by around a factor of 2. So in this table here, I'm showing on the right-hand side our constraints on the merger rate for binary neutron stars from GWTC 3, which was our last catalog release. And the different rows show our different models together with their uncertainties. And then on the left-hand side is now our updated constraints on the merger rate. And you can see it's sort of gone down uniformly by about a factor of 2. However, I also want to emphasize that these numbers are still consistent with our GWTC 3 constraints, because we have large error bars to account for all the different uncertainties. And so, sometimes people ask, should we be surprised that we haven't seen any merger binary neutron stars? And this is telling us that we shouldn't be surprised. We were just maybe a little unlucky. And then I'm not showing it here, but we also have constraints on the binary black hole merger rate, which we measure to much higher precision because we have many more detections of binary black holes. So that's between 14 and 26 mergers per cubic gigaparsec per year. And then the neutron star black hole merger rate is between 9 and 84 mergers per cubic gigaparsec per year.
Debo 3.
So we now have only one new neutron star containing event in O4A, which is GW230529, which is a mass gap neutron star black hole merger, and it's the main driving factor to our conclusions, which means conclusions from the previous GWTC3 is largely unchanged. We do have an inferred peak around 1.4 solar mass, but the constraint is much poorer than what we observe with the galactic binary neutron star systems and neutron star white dwarf system. But we have to remember in the
Debo 3, your voice is not very clear.
Is it better now?
No.
Okay, just give me 1 second, please. Can you hear me better?
Yes.
Okay, thank you. Okay. Yep. So we have an inferred peak of around 1.4 solar mass, but it's much poorly constrained than what we observe from the galactic neutron star systems. But we have to remember we have an order of magnitude lower mass measurements of these systems than from the radio pulsars. There is obviously greater support for higher mass neutron stars than electromagnetic observations. That suggests the minimum black hole mass from the neutron star black hole systems driven by 230529 is about 3.4 solar masses, which remains in the previously named putative lower mass gap. This may have astrophysical implications of how core collapse supernovas occur, because previously it was believed a very rapid core collapse supernova that gives rise to the rapid explosion giving rise to a less than 2 solar mass neutron star, or a complete collapse giving rise to greater than 5 solar mass black hole. So obviously that is not happening, which means we might need to readjust our understanding of the astrophysics behind it. Yep.
Thanks, Debo 3. So in the rest of the talk and the webinar, we will be taking a closer look at our largest source population, which is the population of binary black holes. And I'll be starting off with the discussion of the binary black hole masses. So what you see on your screen right now is basically the mass distribution of binary black holes. This is the primary mass distribution, that is the more massive of the two objects in the binaries. And the first thing that you can immediately notice is that the mass distribution is not smooth. It has a lot of features. It has bumps and wiggles at various places. And the intention is for us to put out these results so that people who work on the astrophysical aspect of these sources can sort of try to dissect each of these features in detail. So let me walk you through a few of those that immediately are visible here. So the first feature that is extremely striking is this global peak of the binary black hole mass distribution at sorry, can you see the slide?
Yes.
Okay. Okay, great. Sorry, just wanted to check because there was a message in the chat. Okay, so there's a global peak of the mass distribution at about 10 solar masses. This basically says that the 10 solar mass black holes are the most abundant black holes merging in the universe. But also, if you look at the rest of the mass distribution, there's a lot of other features. For instance, the one other feature that stands out is this sort of smooth power law-like behavior, where essentially the mass distribution goes as m to the m raised to some power alpha. And this, we see that the mass distribution is kind of shallow at low masses. So I'm referring to this feature here between about 10 and 30 solar masses, but has a steeper fall off, say, about 35 to 40 solar masses. They're also in this weakly modeled approaches, which is the blue plot here, where we use a model that is constructed using splines. We find that there is some possible overdensity or some possible small peak at about 20 solar masses, although this is not very robust against model variations because we did not find it by using a strongly modeled approach. There is a feature at about 35 solar masses, and this is either an overdensity or a peak in the mass distribution, or it's just a transition point between these two shallow and steep features at low and high mass respectively. So it's something like a break point or a transition point between these two power law-like features. And the other thing to note is that there is a non-zero rate about 60 to 70 solar masses. Now, this is really interesting because a lot of astrophysical theorists and simulations had predicted that there should be no black holes that exist in this mass range. And this has to do with specifics of how supernovae operate. Black holes are dead stars formed through supernovae. And so there are certain classes of supernovae called the pair instability supernovae, which essentially do not leave behind any remnant after they go supernova, which means there might not be any black holes about 760 to 70 solar masses. But the fact that we are seeing them means that there needs to be some mechanism to sort of overcome this pair instability supernova feature, either by, say, two black holes merging together and then another black hole merging, such so-called hierarchical mergers that populate this portion of the mass spectrum here. Okay, since we have looked at the primary masses already, we can also try to look at the mass ratio distribution of mergers. And with the strongly modeled approach, which is this orange/red line in this plot, we find that the mass ratio distribution follows a power law kind of structure. So essentially, the mass ratio distribution goes as Q to the beta, where Q is the mass ratio, with beta about 1.2 with some error bars around that. Essentially, what we're saying is that the mass ratio distribution is consistent with being mass ratio distribution is consistent with being monotonically increasing as a function of mass ratio. There are more Q equal to 1 systems than there are Q equal to, say, 0.4 systems. However, when we apply a weakly modeled approach using splines, we find that there is evidence for a mass peak in the mass ratio distribution away from 1, closer to, say, 0.7 or so in this plot. And the merger rate actually drops as a function of Q to larger values of the mass ratio. We also check, we also try, because we have already seen these a few features in the data, we also try to check what the mass ratio distribution of each of those features is. Like, for instance, for the first, we ask what is the mass ratio distribution in the 35 solar mass feature and compare it to the mass ratio distribution in the rest of the black hole mass spectrum. And what we find is that the black holes in this 35 solar mass feature prefer merging with black holes of similar mass, essentially black holes which are other 35 solar mass black holes, and the mass ratio distribution actually peaks at Q equal to 1. But when you check the rest of the mass spectrum, like this orange shaded region here, we see that has less preference of merging at Q equal to 1 and spans a wider mass ratio range as compared to the 35 solar mass feature. Similarly, if we ask the same question about the the 10 solar mass feature in the plot on the right, we see that and this is using a weakly modeled approach, we see that the black holes in this 10 solar mass peak prefer merging with lighter black holes, such that the mass ratio distribution peaks at about Q of 0.7, as is shown in this blue lines in this plot. Okay, Simona, you want to take over?
Yeah, hi. I will be talking about the spin distribution of the binary black hole population. A little bit of background, since spin's a little bit less intuitive than the mass. So spin of the black holes is the sort of second fundamental property, aside from mass, that we can observe. They are the intrinsic angular momentum of each black hole, and we parameterize them in a unitless formalism, where these spins are vectors that have magnitudes between 0 and 1, where 0 is a non-spinning black hole and 1 is the maximum spin that that black hole can support for its mass. And we look at some angles, specifically the one that we care about for the population is this polar or tilt angle theta, defined between 0 and pi. This is the angle between each of those spin vectors and the orbital angular momentum of the binary. For truly understanding the underlying astrophysics of these systems, we do want to measure all 6 spin degrees of freedom, so the magnitudes and the various angles for these vectors. However, these are actually not the parameters that most impact our data. So we also look at these effective spin parameterizations, which we can measure better. So these are chi effective and chi p. The equations are given here, but the summary is that chi effective characterizes how aligned those spins are with the orbital angular momentum, while chi p defines how misaligned they are, leading to precession of the orbital plane. In GWTC4, we use a truncated Gaussian distribution with our strongly modeled approach and infer its mean and standard deviation. This is a change from GWTC3, where we used a beta distribution, but we've decided to move away from this to relax the assumption that the distribution has to be 0 at its boundaries. And for the weakly modeled approach, we use the basis splines model. For both of these models, we assume that the primary and secondary spins are identically distributed, identically and independently distributed, and we also find that the data prefer this. Some features of the spin magnitude distribution that pop out are that for the first time, we're seeing very strong support for there being some amount of spins that are near 0. This was not actually allowed in the model before, so it's good to see that when we relax that assumption that actually this is worth doing. We find that most binary black holes have spin magnitudes of less than around 0.6. The distribution peaks around 0.2. And the 2 different modeling approaches find slightly different things for high spins, with the more flexible spline model finding more highly spinning binary black holes than the more parametrically constrained Gaussian model. Based off of the data, we do believe that this is probably real, and that there is a subset of binary black holes that are very highly spinning. Additionally, we can also model the spin magnitudes of the 2 black holes separately. And the way that we do this is through what's called spin sorting. So we basically take the Gaussian spin distribution from the previous slide and impose that ordering statistics such that one of the spins is larger than the other. And when we recast the results in this formalism, we find that at least one binary black hole, or one black hole per binary, has non-zero spin. Next, we're going to look at the degree of misalignment in the population. So here, our strongly modeled approach is a mixture between a truncated Gaussian distribution and an isotropic distribution. We also changed this model slightly from previous catalogs, where in GWTC3, we fixed the location of that Gaussian component to be at cosine theta of 1. Now we allow this to be a free parameter. And for the weakly modeled approach, we again use a sum of B-splines. We we still find, which is consistent with previous catalogs, that there's a broad support for a broad range of spin tilts in the distribution. So lots of different degrees of alignment between spin and orbital angular momentum. But for the first time, due to our updated model, we find that the distribution may peak away from perfect alignment, meaning that that most of the spins, or sort of the highest percentage of spins, are actually not perfectly aligned with the orbital angular momentum, leading to thoughts of some sort of dynamic formation channels at play. And finally, we also look at the effective spins. As I mentioned previously, these are what are better constrained in the data. And for these, I'm only showing the strongly modeled approach. And for the chi effective distribution, we use a truncated skew normal, which adds another degree of freedom from the GWTC3 just Gaussian or normal distribution. And for chi p, we use just a Gaussian distribution. One of our main conclusions is that we find that the chi-effective distribution is skewed and asymmetric about 0, with more support for positive chi-effective than negative chi-effective. You can see this in the shape here on the left. Additionally, we find that the chi-p distribution peaks around 0.3, with more support for large chi-p than there was in GWTC3, although this is somewhat sensitive to some specifics of the models that are used. But the takeaway here is that there is some amount of spin precession happening in our population, which is also reflected with our spin tilt results from the previous slide.
Okay, yeah, so I'll be talking now about the binary black hole merger rate as a function of redshift. And real briefly, we basically see that the binary black hole merger rate increases as a function of redshift. And so parameterizing this in our strong model approach, we just model the merger rate as a power law in 1 plus the redshift z. And we infer this power law index kappa. So on the upper panel, you can see we're comparing the inferred value of kappa in the dashed unfilled histogram, which maybe had a tail towards 0, which was a tail towards no evolution with redshift. But now in GWTC4, we confidently find that the merger rate is increasing with redshift, so kappa is positive. Once again, we use a B-spline approach for our weak model, and this approach also finds the merger rate is increasing as a function of redshift, but it's consistent with our strong power law model. It's also consistent with the increasing star formation rate that we see in the universe. This has a power law index in the local universe at about kappa of 2.7. So we are consistent with that. Yeah, finally, we see that the merger rate at redshift 0.2, which is where we are most constraining, is at around 30 mergers per cubic gigaparsec per year.
Thanks, Jack. So in the last part of this webinar, we will be discussing about correlations between source parameters. So far, we've dissected single quantities on their own, but in this section, we will try to sort of ask how do the quantities vary with each other. So for instance, the first question that we wanted to ask is, does the effective spin distribution change with mass ratio? This has been discussed in the literature for at least about 5 years right now, that there was a variation in the effective spin distribution with mass ratio. So to sort of probe this, we allow the peak location and the width of the spin distribution to vary with mass ratio and sort of see how the variation what the variation looks like. So before GWTC4, the way that this variation looked like was that the mean of the chi-effective distribution was known to vary very strongly with Q. In other words, as you increase Q, as you go towards the mass ratio of 1, you would see a lower mean of the chi-effective distribution. But in GWTC4 with more data, we find that it's not necessary that just the location or the mean of the peak of the chi-effective distribution varies with redshift, but it could be either the location or the width of the effective spin distribution should decrease with mass ratio. This is what is shown in the plots on the right. The blue sort of traces are the ones that denote this linear model, the strong model that we use in this for this analysis. We see similar trends with a weakly modeled spline approach, as is shown in the orange plot on the right. Similarly, there was a correlation that was discussed in the literature of the effective spin distribution with redshift. And so similarly, what we do is see if the location and the width of the effective spin distribution varies with redshift. And we recover previous results in the literature that the width of the effective spin distribution, this quantity sigma effective of Z, actually increases with redshift, whereas there's approximately no change in the location of the peak of the chi-effective distribution with redshift. Great. The other thing that we also tried to ask is, does the effective spin distribution actually change with mass? This is motivated by the feature at 35 solar masses. And so what we do is we infer the effective spin distribution between 30 to 40 solar masses so that we can include this 35 solar mass feature, and then also outside this range using a weakly modeled approach, which in this case was the bin Gaussian process. And we find that black holes with mass between 30 to 40 solar masses have smaller effective spins than the rest. This conclusion, I should say, is a bit model dependent, but the way you can see it in this plot is by noticing that say for instance, the orange histogram actually extends to larger positive values of chi-effective as compared to the blue histogram, which denotes the mergers between 30 and 40 solar masses. Okay, so let me conclude. So as you've heard from our wonderful speakers, we analyzed the population of merging compact binaries in GWTC4. We uncovered a lot of new features in the population and also refined the statistical significance of previously reported trends. Several of these features actually pose challenges for understanding the formation mechanisms of these binaries, and that's where all the our hope is that the community will take these catalogs and sort of dissect it to sort of understand the formation mechanisms of these binaries. But I also would like to remind you that this is only using data from GWTC4, which is only the first part of the fourth observing run. The data from the rest of the observing run will actually increase a number of events, obviously, and then further enhance our understanding and may also uncover additional structure in the population. So stay tuned for these results, and thank you, and we're happy to take any questions. Okay. So I imagine you can put your questions in the chat or also ask to unmute. Is that right, Casey?
That sounds perfect. Folks have also used the raise hand feature to signal that they do have a question. So if you could use that raise hand feature, I'm happy to unmute you so that you can ask your question. We also do have a question that's been placed in the Q&A.
Sorry, let me just try. Okay, there's a question from Filippo Santoliquido. What kind of biases do we expect from data collected during the engineering runs? So Shio, since you were talking about this, do you want to answer this question?
Yes, Filippo, thank you for your question. Yes, so for the engineering data portion that was made public, going back, we typically do not make the engineering part of the data public because not everything is set up to engineering run data is not something that we expect to put out into public. It is more for our internal testing. However, we did make about 4 days of data, I believe about 4 days of data public for this particular event, this NSBH event that was detected during the engineering run for the interest of the community. Therefore, within the duration of the engineering run, a certain portion of data was selected to be made public. So if we were to include that data in our analysis, there is a selection effect. Humans are selecting a portion of the data. So that would be adding a little bit of bias to our analyses, and we wanted to avoid that. Does that answer your question?
I think that was a great answer, Shio. Thank you. Filippo has two more questions. So the first one is, what is simple uniform BNS merger rate density? And I think this is about the rate slide that Jack presented. So Jack, do you want to answer this?
Yeah, absolutely. Yeah. So in our reconstruction of the merger rate, there's two sources of uncertainty that contribute. One of the sources of uncertainty is we've gotten random Poissonian realization of the underlying true merger rate. And we've just seen two binary neutron star mergers. And so what does that tell us about the true merger rate in the universe under this Poisson uncertainty? So that's one of the levels of uncertainty. The other level of uncertainty is the actual shape of the binary neutron star distribution. And so our two models, the full pop and the BGP, allow the shape of the binary neutron star distribution to vary. And so this adds on an additional layer of uncertainty. So this simple uniform BNS model was basically just designed to say, if we only care about the Poisson uncertainty and we just say that the binary neutron star merger rate is just uniform between 1 and 2.5 solar masses, what does that tell us? Like, what is our reconstruction of the intrinsic merger rate? Yeah.
Thank you. Thanks, Jack. Another question that Filippo has is, why does the mass ratio drop at Q equal to 1 for weakly modeled approach? So Filippo, the answer to this is, okay, for the strongly modeled approach, we actually do not have flexibility in the model to actually capture things like a drop in the mass ratio distribution above a certain value because it's a power law, and by definition, power laws are monotonic. In the weakly modeled approach, the Q equal to 1 feature we believe is real, and it has also been recovered by sort of other analyses in the literature. And now, what the astrophysical reason for this is anybody's guess, and I think there needs to be more sort of work on this to understand why. One hint that is already present in the slides that we presented was that the mergers in the 10 solar mass peak prefer to have a peak of the mass ratio distribution about 0.7. So it might just be those mergers contributing to this sort of sudden drop in the mass ratio at about Q equal to 0.7 as well. Another attendee has a question: how do you account for selection bias while constructing for example, the mass distribution? Ben, since you talked a bit about selection effects, would you like to take this?
Sure, happy to. So selection effects are always tricky in astronomy, and within gravitational wave astronomy, specifically looking for compact binaries, we are super fortunate in having both very predictive models for what our signal looks like according to general relativity. We have a very clear picture of what we expect a gravitational wave signal to look like from a given binary merger with some masses, spins, etc. So that, coupled with our ability to have lots of different realizations or observations of what noise looks like by, for example, artificially sliding in time the data from our different detectors. We have gravitational waves that pass through the Earth. The signal should show up when there is a signal between different detectors and less than or equal to the amount of time it would take light to travel between our detectors. So we can artificially slide our data streams to create, by definition, noise. And so we can take our model for our signals, put them into real detector noise, and then run all of the searches on that noise containing simulated signals to look for whether or not we would expect to detect such a signal astrophysically. And so we do exactly that. We take the data that we collected during the observing run, we simulate signals across the parameter space, and then we plug that simulated data plus real noise into each one of the searches that are running on the data, and assess the sensitivity of each of those searches across the parameter space. And then we put that all together in that hierarchical Bayesian inference framework that I described before, to effectively downweigh the parts of parameter space that we are overly sensitive to, and increase the significance of detections that we have in parts of parameter space that we know that we're less sensitive to. If you're curious in our more details on our search techniques, I encourage you to, I think, look through the YouTube channel for the previous webinars on GWTC4, where some of the details are discussed there.
Thanks, Ben. There was a question in the chat about what the distance range for these mergers from O4 is. Obviously, and this was asked by Mark. Mark, so the answer to this is that it depends on what the mass of the signal is as well. So for lighter systems like binary neutron stars, we can only detect them up to a few hundred megaparsec away. Unfortunately, we didn't have any of such dissections in O4. But for binary black hole systems, which can get as massive as, say, 100 or 200 solar masses, we could detect them out to really high redshift of 1 or 1.5, which is about roughly order of 5 to 10 gigaparsec away. Yeah. Open. I don't see any open questions in the Q&A or in the chat. So, but if you have any, please feel free to put them there. Okay, we have a new question from Peter. So the question is, do these population results tell us anything about the formation channels and the merger environment? So I can start answering this question, but for anybody in the panel, if you have any other perspectives on this, please feel free to go after me. So yes, the whole point of us trying to do these population level analyses is to sort of learn about formation channels and the merger environments of these sources. The hope is that say, for instance, certain features in the mass distribution might tell us something about how those black holes of those masses formed. For instance, one explanation for this really prominent peak at about 10 solar masses is the process of stable mass transfer in binary stars. So essentially, binary stars that are stably transferring mass to each other and hence co-evolving, and then sort of collapsing into black holes and then merging. There's also, as I mentioned in one of the slides, in the mass distribution, there seems to be a non-zero merger rate, about 70 solar masses. With this is challenging for our theories of, say, pair instability supernova mechanisms, where the supernova does not leave behind any black hole. These are really massive stars, which when go supernova do not leave behind any black holes. So you should ideally see like a cutoff in the mass distribution, but we do not see that. There have been other recent lines of evidence which show that while the cutoff does not exist in the primary mass, it does exist in the secondary mass. It could exist in the secondary mass, which might tell us something about how these systems formed and evolved. And finally, the black hole spins, for instance, tell us about the merger history. One way to understand this phenomenon of hierarchical mergers, where two black holes merge with each other, form a bigger black hole. This black hole is typically highly spinning, and then that black hole goes on to merge with another black hole. In this process, the spin of the system would increase just because one of these black holes is really rapidly spinning, and that will show up in our spin distributions, or the effective spin distribution, also the precession distribution, and so on. But hopefully that answered your question. But does anybody on the panel want to add to what I said?
I can chip in a little bit, and because we have populations emerging now instead of just individual events as it started about a decade ago from now, we might also want to highlight sometimes there are correlations between, say, a mass of an event that we observe or a bunch of events that we observe versus the spins, because all these formation channels, astrophysical formation channels, there are certain uncertainties that can be constraints, but also can sometimes be degeneracies if we are looking at only the mass or, say, the spin, because sometimes spin misalignment, although some people say can come from hierarchical mergers or mergers in really dense stellar clusters, where black holes can interact with each other from different directions, different gravitational perturbations. You can also have supernova kicks, for example, that misalign systems, and the tides that occur in star revolution may not be very strong to completely realign systems through isolated binary evolution. So there you want to look at, say, mass ratio, individual masses, spins, and a combined effect of different correlations together that we are getting to do more often with the populations emerging in our catalogs.
Thanks, Debotri. Any other perspectives from the panelists? Okay, I don't see any. Let me check the chat and the Q&A box for more questions. Don't see any, but I think we have maybe a few more minutes for questions. So please feel free to put them in the Q&A box. Okay, I do not see any coming in. So maybe that's a good point to sort of, since we're also at the top of the hour, maybe that's a good point to stop this webinar and thank everybody for attending. I also want to leave you with the large acknowledgement slide that we have for each of our papers, which basically tells us that, yes, we are like 5 or 6 of us who are on this call answering questions, but really it took a village to actually make this science possible. And so there are scientists from many, many different countries and thousands of them actually who work to make this science possible. So thank you for attending.